Masters,
ठीक है ना मास्टर्स क्लास ओके स्टार्ट
so this is our well optimization project. So here our objective is to develop an intelligent system that optimizes our oil well performance using machine learning techniques, combines petroleum engineering principles with data science to maximize the production and economic returns. So what exactly is the problem statement? We'll try to understand. So oil wells have varying performance due to its reservoir properties, operational parameters, and economic factors. And manual optimization is very time consuming and may miss complex relationship between different parameters. So that's why we need an automated system to identify optimization of opportunities and predict performance improvements. So what will be our solution approach here? So well optimization, this is our project. We have the data from a mature field. You can say well IDs are there, permeability, porosity, net to gross, thickness, well depth, tubing diameter, choke size. All these data is with us. Okay. Reservoir properties are there, permeability, porosity, IPR properties are there, productivity index, pressure drawdown, oil rate, well-designed parameters are there, tubing diameter, choke size, well depth, and operating conditions are there, drawdown pressure, water cut, bottom hole pressure. Apart from that, economic factors are also there in in the data, in our data. So we have daily revenue, that is basically a mixture of oil revenue, gas revenue, and here it is daily OPEX used, gas price, oil price, all these things are also present with us. So there is this daily revenue that take the account of oil revenue, gas revenue, and operating cost. Okay. So these data points we have for a standard field, for a tight oil field, for a simple well, and for a mature field. We are going to use these particular data points. This is the data analysis of our data, quick idea of our data, water cut impact on production. So if oil rate, water cut is always present, little bit of water rate is always present, no matter what is the oil rate. Even if the oil rate is very high in that particular situation, is also a little bit water cut is present. Porosity versus permeability plot is there. Oil production rate distribution. A left, right skewed oil production is there. Oil rate has a direct impact, 45-degree impact on the daily revenue. Obviously, if oil rate is increasing, our daily revenue will be increased. So we have horizontal type of well, vertical type of well, and deviated type of well. And different oil rates are there, each of them. And we also have different artificial lifts present in our data: gas lift, road pump, natural flow, and ESP. ESP is having the oil rate at on the higher side. And yeah, you can go through these particular plots. Now, what we are going to do? First of all, I also given the data if, for example, I also have a data preparation.py file. If you do not have data with you, you can create a realistic well data based on the petroleum engineering principles. So I'm not going to cover this because we already have data with us. So this is a synthetic data generation file that is present. You can use it if you want to play around the data. Okay. And then we have, after that, we will understand the relationship between different variables using EDA. So this plot will be generated from the EDA itself. And after we'll train our machine learning models to predict the well performance, then we'll use these models to recommend parameter improvement. And based out of those parameter improvements, we are going to evaluate the final impact on the optimization. Okay, so it's a regression type of problem. We have to predict, basically, we are predicting continuous well performance index. Well performance index is basically oil rate. Let me show you the formula. So this will be our target variable, that is performance index, that is oil rate into 1 minus water cut into oil price divided by daily OPEX into 100. Okay. Some of the feature engineering will do, and then we'll be training linear regression, random forest, and gradient boosting. Okay. So let's start the code walkthrough for well optimization project. So we have an initial class here, well performance optimizer class, in which basically we are reading our well data that is present here, well data.csv. And then there is a load data function that will be loading the well performance data from different CSV files. And just a second. After that, we have the EDA functionality. It will perform the comprehensive EDA on the well data that we have provided. Okay. So data, basically it will plot different things for us. It will be plotting oil rate, histogram of oil rate that you just saw. This particular PNG file is generated from this EDA analysis code only. Okay. So it will try to understand the well performance spread by using the histogram. Then there is your performance versus permeability plot, this particular one. Then we have water cut impact. Basically, a negative correlation is present with the oil rate. Then we have pressure analysis, drawdown effect. We have economic performance, revenue versus performance. Here it is revenue versus performance. We have choke optimization, optimal operating ranges. So we performance is there, choke optimization. Yes, that node is not present here. Then correlation matrix is present here. We can see that this daily revenue, performance index, and oil rate, these are highly correlated with each other. So these will be the different EDA steps. So basically, we are generating these different plots: water cut, performance index, pressure analysis, economic performance, job size optimization. Job size optimization, correlation heat map, performance distribution, top versus bottom performers. Okay. And after that, the next method is our machine learning pipeline. So we will be preparing the ML features here, feature engineering and preparation for a machine learning model. Okay. So here in this particular part, we are creating these new features: pressure drawdown, productivity factor, economic efficiency, and total fluid rate. All depending on the physics-based analysis of our data. Okay. Then we are going to use these particular features only for our training part. These will be our X values. Y value will be my performance index. So here in this particular thing, we have selected based on the petroleum engineering principle, we have selected the feature. We included the raw measurement and engineered feature. And we have a target variable with us, that is our performance index. After that, our training code will come. We'll train and compare multiple machine learning algorithms. So in the starting, we are just splitting our data into train test split. We have machine learning, linear regression, random forest, and gradient boosting models that we are going to train. Feature scaling we have done here. All basic things that we generally do in any machine learning project. And then here, our model training is starting for each particular model that is present here. Okay. So we'll be training a linear regression model, random forest model, and gradient boosting model. And once these are done, we are storing the result from each particular model, basically evaluating the model. So MSC, RMSC, MAE, and R square score, these scores are stored. And out of these particular scores, we are selecting our best model with the highest R square score. And we are going to store that particular best model for the later use for inference, basically. And we are also getting the feature importance here so that we must know which feature is important. We are getting the feature importance from our decision tree model, okay, a random forest model, because tree-based models only have this feature importance thing. After that, we are going to plot our model result. Basically, we'll be plotting the R square comparison, RMSE comparison, prediction versus actual graph, a diagonal line that will show the perfect prediction, scatter points close to the line is equal to good prediction, and systematic deviation indicates model bias. We are going to show it. Once I run this code, I'm going to show this. Okay, so all the results will be plotted here in this particular function. Then comes our optimization function. So it will generate the optimization recommendation for underperforming wells. Okay, it will target the well selection first of all. If target well is none, it will select the bottom 10% performers for the optimization. So it will basically focus on the worst performers, so that is basically our biggest opportunity. And after that, it will at least have 10 wells to ensure meaningful analysis. And then it can specify specific wells to optimize. Then our optimization loop will be running here. This is our optimization loop where we'll be getting the current well parameters, we'll generate the optimization scenarios, we'll predict the performance for each scenario, and we'll select the best improvement here. Current parameters we are getting, then optimization scenarios are generated. This generate scenario will be coming below. And after that, we'll be predicting. We'll be predicting the performance for each scenario. And then we are going to select the best scenario. The best scenario. Okay, then we are predicting the current performance, optimized performance, improvement, and best scenario here. Just like that. And then comes our this generate optimization scenarios, that basically the function that we used here for creating realistic optimization scenarios based on the engineering practices. Okay. So we'll try to optimize the choke size, we'll try to reduce the water cut, we'll try to maintain the pressure. So optimizing choke size, basically we'll try to increase choke size to allow more flow. Maximum choke size is 64 by 64 inches. And 50% increase is a really realistic operational change that can be done. Then there is our water water cut reduction here. So we are trying to work over operations to reduce the water production. Minimum 5% water cut is a realistic limit. And 30% reduction can be achievable with a good workover. Then we are trying to maintain the pressure maintenance here. So improve artificial lift or reduce wellbore pressure losses. Bottom hole pressure must be less than reservoir pressure and keep 100 psi minimum go down. Okay, now comes our economical analysis function. It will perform detailed economic analysis with the profitability inside. Okay. It will analyze the economic performance and identify improvement opportunities. So basically, it will be taking in the account the daily revenue USD And from that, it will be finding the positive daily cash flow, and small losses through the modest profits can be taken care of. And it will help in prioritizing the optimization effort. So all that thing is done here in this particular thing. Here, this particular break-even rate, this is a key matrix calculation. This is basically the production needed to cover the operating cost, that basically the cost that we are applying, how much production is needed. So that is this break-even rate. Unit of this is barrel per day, obviously. At what rate should I produce so that I'm at the break-even? Then we are also doing the loss analysis here. We are trying to identify the losers well, the one that have a negative cash flow, the wells with the negative cash flow. And we are calculating the total annual loss from those particular underperformance. And these wells need immediate attention. We are doing that for the immediate attention. Then comes our reporting function. It will generate a comprehensive optimization report with the executive summary with key insights and recommendation. So complete data summary will be shown here. Overall field performance, diversity in well performance, one decimal place for readability. Okay. Then comes our model. Where is our model performance section? This is our model performance section. It is showing which algorithm performed the best with the high R-square score. Then comes our economic opportunity section. This will basically show the wells that are bottom 25% of the wells. Okay. And we are calculating the revenue for them. And we are doing the realistic optimization potential for them. Then comes our performance insight section, this particular one. It will compare top versus bottom performance. It will show the improvement potential and best practice for top performers. And last one is this one is our recommendation section. Basically, it is providing the specific steps to implement actionable items, what need to be prioritized, and complete technical and economic recommendation. Then comes our strategic function that will develop a field-wide optimization strategy, field development strategy. So here, basically, we are segmenting our wells by the profitability to profitable, marginable, and unprofitable well. Okay. $100 per day separates profitable from the marginal. So that proper resources will be allocated based on this well categories. That's why this well segmentation we are doing. We are also identifying the sweet spots here. Basically, the one with the higher permeability and low water cut with the high performance. These are the best areas for the new drilling. That's why these sweet spots are identified. High permeability, low water cut, and high performance. And this is our data, means data generation function there that we already have separated into this data preparation file. So I'm not going to discuss this because we already had the data. So this one is the function that will create the dashboard, the .png for us for optimization insight. I'll show you once I have this particular thing. So basically different plots will be shown here using this function. Okay. Now this is our main execution flow. It will orchestrate the complete analysis and workflow. So here we are, first of all, if we are importing the OS, we are seeing if our CSV file is present or not. If CSV file is not present, then it will generate the data set. Otherwise, it will go with it. Then we are initializing our optimizer with the CSV file. Then sequential analysis steps are coming, loading well data, performing EDA, training machine learning model, performing economic analysis, optimizing well parameters, generating a comprehensive report, then developing the field strategy, creating the optimization dashboard. The complete flow in which we have gone. Okay, so now let's run it. Let's execute the script and let's see what exactly is happening here. The full analysis pipeline will run now. We'll create a data if needed, but we already have the data. That's why it's not creating the data. Here comes our first plot. This you already have seen EDA dashboard. Oil rate versus water cut, average oil rate, top versus bottom performance, top 50% bottom 50%. That's what is the difference in between their job size, water cut, and permeability. Performance index distribution, correlation matrix. So this is a quick EDA. So now our machine learning model is being trained. These are the machine learning models result. Best one is your linear regression only. As compared to RMSE, R square score is not coming good for this. We need to see that. Then comes our this thing for random forest, it's fine, and these are the feature parameter. Productivity factor is the most important feature here. Then comes our pressure drawdown, then comes our water cut fraction, permeability, oil gravity, and stuff. This is our well optimization dashboard. So you can see the profitable well counts versus oil price in barrels. So if oil price is increasing, how many wells will be in the profitability? If it is $50 per barrel, then only 400 wells are in profitability, otherwise 500. There is ROI, return of investment versus production rate. Production rate is high, your ROI will be high. Daily revenue versus performance index. Porosity versus permeability, simple graph. Well ranked graph. Top 20 optimization candidates, which one are them? And production versus water cut. So done. This is the complete summary. We trained the model. We saw the most important features. Then we performed the economic analysis. Around 97% are the profitable wells, 23% are marginal wells. Average daily revenue is $354. OPEX is $254. Break even oil rate is 3.5 barrel per day. 14 wells are operating at loss. Average daily loss is $32. Total annual loss is this much. Huge. And then we are performing the optimization on the loss on the loser wells. Current performance was 51.1. Optimized performance can increase to 146.9 by reducing the water cut. This is also for water cut. This is for combined optimization. Again, water cut. Again, water cut. And this is the complete well performance optimization report. Production range is between 5 to 192. Average performance index is 183. These many are profitable wells. This was the random forest R square score. It's very low. You can improve it by tuning the hyperparameter. Annual revenue increases this much by changing the parameters. Yeah. And these are the recommendation. Focus on choke size optimization for immediate gain, implement water cut reduction, consider pressure maintenance, regular performance monitoring, prioritize optimization of well with intention. This is the complete field strategy here, well classification, profitable wells, what are the recommendation for them, marginal wells, what are the recommendation, what are for unprofitable wells. Then sweet spot identification, 51 areas have been identified, average performance is this, average production will be. Then the dashboard we already saw, then a little bit of economic sensitivity analysis is also done here. Basically, we are testing different oil price environments. Okay, what will be the revenue at different oil prices? That thing is tested here. Simple what if conditions, what if scenarios. That's it. Here is your this particular project. Now, that is your well optimization project.